Okay, so hi everyone. So today I will explain about mechanics of material, chapter 3, which is shear force and bending moment. Okay, so for this chapter you will learn about two outcomes, which is first you can draw the shear force and bending moment diagram, and then you will from the diagram you will you will determine the largest shear and also moment, okay, in the member and also the location of it. Okay, so let's go to the introductions. So change of shear force and bending moment in beam as reactions to several types of loading, including the uniform distributed load, point load, moment, and so on, or either combinations of different supports. You have cantilever, you have pin, you have rollers. Okay, so value of shear force and bending moment as well as the locations of the maximum values can be determined. Okay, so this maximum value important because they will be used in the analysis of structural design, so we need to have the maximum values to know that maximum force, maximum reactions that needed. Okay, so you can see this is a beam. Okay, this is a beam. When you apply the load on it, okay, so what will happen? Okay, so this is roller support. Okay, roller support, and this is beam. Okay, you will have a load or brake on it. So when you apply the load like this, when you have a roller only support from the y directions, so will it be equilibrium? Okay, so how to make this system to be balanced? So imagine you put a plate on a two rod. So when you push from the left, okay, it will move towards here. It will not stay in static. Okay, so this is not in equilibrium if so. Okay, so let we go through the types of beam. So beam can be defined as structural component that has a smaller dimensions of cross sections than its length. Okay, because beam you will have this kind of sections. The length is big, but then the dimension, the cross section is only this small. Okay, only this. So you will have two types of the beam, which is the statically determinate beam and statically indeterminate beam. It is statically, okay, but then they have two types. We have statically determinate beams and also statically indeterminate. Okay, so this classification of beam depends on the unknown of total reaction force, okay, to the static equilibrium equations. So there are three equilibrium equations classified into two types based on their analysis. Okay, so now the classifications, we can see that from here. Okay, it depends on the total unknown. Okay, total unknown of reaction force to the static equilibrium equations. So we know there are three equations. Okay, you need to remember this. Okay, Fx equal to 0, total Fy equal to 0, total moment equal to 0. So when these three are in 0, so it will stay in static equilibrium. Okay, so if unknown total reaction force is more than 3, so let's say your unknown is more than 3. Thus, the beam is statically indeterminate. You cannot determine if you have more than 3 unknown by using this one, because there is only 3 unknown. But if you have, let's say you have 4 unknown, for example, you have a beam with 2 pin. So you have 4 unknown instead of 3. If let's say 3 is you have 1 pin, 1 roller, this one is 3 unknown. So this one is statically determinate. This is statically indeterminate. Okay, so you can see that the reaction force here, the equation, this one is important also. Okay, so R is less than 3. So for example, if you have a beam on a roller, so roller is reaction force is 2. Okay, 2, and number of joint is 0 lah. So let's say this one reaction force is 2 less than 0 plus 3, so it's not stable. Okay, so if let's say this equation, you can refer to this one. Okay, so statically determinate. Okay, R is equal to 3, joint you don't have, so 3 plus 3 is equal to 3, so it's statically and also determinate. So you can calculate using these three equations to get the reaction force. But then when this one, okay, R is greater than n plus 3, so 4 is greater than 3, okay, so it is statically, okay, it's statically stable and so on, but then it's indeterminate. You cannot get it from these three equations because your equations is only 3, but then your unknown is 4. Okay, so example, type of supports here. Support reaction, the reaction can be determined according to its support. So first, okay, you will always see this is simply support. So this beam, you can see that here is pin, here is roller. So this one you have 2 reactions, this one you have 1 reactions. Okay, so this is statically determined, and the load here you can see is applied on here, 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 here. You can see, right? Okay, so this is the free body diagram for this picture. Okay, so how's about cantilever beam? So cantilever beam, you can see that the support is at this direction, at this part, and then this is free end. Okay, so free end here you will have force here. Okay, so this one you have a fix here. You have support from here, and also the moment. Okay, so this is statically determinate beam. Okay, so how's about continuous beam? Continuous beam, it has several supports. Okay, it has so many support, you can see here. Okay, so you have pin, roller, for example here. Okay, so you have 4 reaction. 4 reaction is greater than 3. Okay, so you cannot determine with the equilibrium equation. You have another method to do it. Okay, so this is statically indeterminate beam. Okay, so let's go to the type of support. Okay, so when you see the example is in this sketch, okay, so you will automatically know what are the reaction forces for each support. So number 1, you can see you have roller. Okay, roller is in this shape, the round circle shape, so you have only V. Okay, Fy, you can also call this Fy. Okay, so V is 90 degrees to the surface. So when you have pin is, okay, you have 2 reaction force. So you will have Fy, you have Fx, x direction. So when you have fix, you will have Vfy, okay, you will have Fx, and also the moment. Okay, moment toward this direction or that direction is actually similar things. Just when you calculate, you will get the direction. Okay, so also another type is cable. Okay, you will have a beam here, and then it support by the cable, so your reaction force here with incline. Okay, so also we go to type of loading. Type of loading, you will have dead load, live load, wind load. Okay, so this load also, another is you will have point load, distributed load, and also moment loading. Okay, you have so many types of loading. So we go to first one. Okay, so loading is the fixed and very close to the approximate values, very little change. So basically it's the things that is static put on it. So for example, it's like structural weight, ceiling, fixed, so equipment such as a piping system, lighting, air condition. This one you are not gonna move it day to day. It's basically stay at day stably. Okay, so for example, construction elements, please refer to the British standard or either Euro code. So live load and imposed load, okay, or either imposed load, this is variable load, mean it is change from time to time. Okay, change from time to time. Okay, for example, human weight, our weight, future furniture, sometimes you do change the location of the furniture, and other equipment based on the structural purpose. So value for the loading can be referred to BSEN 1991. You can refer to the BSEN lah. So wind load is the building that must account for wind load, especially in high-rise building. So for tall building, you will have wind load. Okay, the effect is quite obvious, okay, quite significant compared to the low-rise building like 1-2-story building, okay, due to the high winds, okay. So however, the effect on wind load is depend on the location, the shape, buildings, dimensions, wind speed in the particular region. So this all we must also consider. Okay, so we go to this load, point load. Okay, point load act on one position only whether in vertical or inclined directions. So the unit of this is Newton or kilonewton. Okay, point load is only by the names, point. So you can see that you have point like this. Also you can have incline. So when you have this one, okay, this load, you will have to break it to two components. Okay, so this is the Fy, this is the x direction one. Okay, so you need to calculate, break it to two. So distributed load, the unit is Newton over millimeter square, or either kilonewton per meter square. Okay, this one is at the certain distance. Okay, so you can see that. Okay, this is the trapezium, sorry. This is the rectangular shape lah, and this is a triangular shape. Also, you will have trapezium shape if so. Okay, so if this trapezium, you can break it to one part, another part, or either you can combine to calculate. Okay, so based on your preference on how you want to do it. Okay, so moment load, resulting load made by a pair of force, and also this force will create moment on the point of loading. So the unit of this load is multiplied with the perpendicular distance. Okay, so it's kilonewton meter or either Newton millimeter. So you can see that for point load is kilonewton. So for this one is kilonewton per meter. This one is kilonewton meter. Okay, two different the unit. Okay, so now we go to reactions on support. So free body diagram. Okay, in order to calculate the reaction from any structure, first draw the actual structure again in the form of a free body diagram. So you must first you have free body diagram. Okay, you draw this, then you will know, you have the idea on how to calculate it. So for example, this one, okay, this one you draw in this way. Okay, so free body diagram is the sketch of actual structure in the line form that are free from supports as well as from loading action on it. So you draw the reaction and support in the direction of the reaction with their accurate dimension. Draw all forces loading acting on the element. Okay, so free body diagram. Okay, you draw in for one line for this beam. Support, okay, A is roller support, so it's only having a VA. Okay, also the B, okay, V, you have a pin support, so you have the horizontal force and vertical force. HB is horizontal, this is vertical. Okay, vertical, horizontal. So the P component you have this is incline. So when you incline, you need to break it to the FY condition. Okay, the Y1, the vertical, and also the horizontal. Okay, sorry. So this is this direction because the force is this way. So you break it to here. If let's say the force is this way, then you break it to this and this directions. Okay, this one you learned in static and dynamic before. So if you're not familiar with incline loading, please make your own study lah. You need to refresh yourself for it. Okay, so after you know how to draw the free body diagram, you've done the free body diagram, then you need to go to equilibrium equations. So with these three equilibrium equations, okay, with three unknown, so you can solve it. Okay, so this concept for raising these equations reaction of certain structure can be determined. To avoid a simultaneous equations, let's use moment equations. MO the moment first. Okay, so you can, from this is recommended to use this one first, followed by other reaction force. Okay, total moment equal to 0, total Fx equal to 0, total Fy equal to 0. So if the solution of these simultaneous equations gives the negative values, means that the earlier assumption of the reaction direction is incorrect and the actual direction is opposite. So for example, you assume the force is in this way. Okay, so when let's say you calculate the Fx equal to 0, and then you get the negative value for this, means that you assume toward this direction is incorrect, and the correct one should be this way. And let's say you assume to be going upward the support reaction, but then you get negative value, so actually your free body diagram should be going that way. So after you calculate the support reaction, before you calculate the the shear force and bending moment diagram, you can sketch again with the correct diagram. Okay, so example 1, determine the reactions of beam stressed by a load as shown in this figure. So you can see that support A is roller support B is pin support. Okay, and then you have uniform distributed load here with incline 10 kilonewton. Okay, and then at 30 degree. So the distance is 4 meter, and 7 meter. So you need to transform this into free body diagram like this. Okay, so you can draw this is VA, vertical force A, vertical force B, HB. So now you assume at this direction, and later when you get the value, you will know that is it going this way or going that way. Okay, so the 10 kilonewton is inclined load with 30 degree. So you need to break it to the vertical force and also horizontal force, as you learned in static dynamics before. Okay, so the solutions. Okay, so you can see this is the free body diagram. Okay, so this is, you can see that we start with using the MA. Okay, so the MA is equal to 0 in equilibrium. Okay, and then this one assume counterclockwise is positive. So at MA, at here, okay, at MA, at point A here, okay, here is point A. So 15 kilonewton per meter, uniform distributed load 4 meter, it will cause a moment at here. Okay, so counterclockwise is positive, assume here, so this is the value. Okay, minus, so from this you can see that this load will cause a moment toward here. Okay, so is 10 sin 30 times the distance 4. Okay, and then you have VB. Okay, so this VB here, you can see that when in the previous slide you are assuming going upward. Okay, so you assume going upward like this. Okay, so it's going this way, so that's why it is positive. Okay, when you assume positive, then you calculate VB, 11 BB, they equal to negative 100. So VB is negative 9.1 kilonewton. Okay, when you calculate and then you get negatives, means that it is going that way. So you calculate Fy equal to 0. You get VA plus VB when you assume, right? You calculate using this free body diagram. Okay, so VA plus BV minus 15 times 4 minus 10 sin 30 degree is equal to 0. 15 times 4, this one, you transform it back to the uniform distributed load. Okay, so VA is equal to minus VB. Okay, you move this to here, everything you carry toward the right side. Okay, plus 10 sin 30 degree. So VB is negative 9.1 from here, plus 60 plus 5, Okay, you calculate, you get VA equal to 74.1 kilonewtons. And then you get VA, you get VB. Okay, so now you go to get the hash. This is the result. This is the result after you calculate the findings. Okay, so total fx equal to 0. So hb minus this going that way. Okay, you going this way is positive, you can see. Minus 10 cos 30 degree equal to 0. So hb equal to 10 cos 30 degree at 0.7 kilonewton to the right. Okay, so this is example 1. So after you calculate all these three, turns out this is the result. Okay, so this is example 2. Determine the reactions on beam. So you need to find the reaction at A and at C. Okay, at A you have RA. Also you can write as VA. C you have VC and also HC. Okay, and then you have force 1000 Newton at B and 500 Newton at D. Okay, these 2 points. So first we will use the moment. Okay, the moment equation MC equal to 0. So assume counterclockwise is positive. You want to assume clockwise positive is also okay. So make sure you applied the correct direction for the moment at the equations. So you are at the point C, you are at here, point C. So while 1000 times 200, so this one you cause a counterclockwise moment. From here you can swing toward here, and then 500 will cause a clockwise moment. You can see that if you from point C, and then RA you going this way, so it will cause the moment clockwise. That's why this is positive, negative, negative. So after you calculate, you get the RA is 200 Newton going upward. So after you get RA equal to 200 here, okay, you have 1500. So RA plus RC minus 1000 minus 500 equal to 0 when total Fy equal to 0. So after you solve this, okay, so 1000 minus 500, sorry, here is 500, so this is 500. Okay, so this one supposedly is also typo here, this is 500, so 500. So this is negative 200. Okay, so 1000 plus 500 minus 200, so this one is 1300 going upward. Okay, so you get the RA and RC already, but HC you haven't get it. So you need to get the total reaction force at HC. Total Fx equal to 0, and then going this way is positive. Okay, so HB equal to 0 because we only have HB one direction at here at horizontal force, but then there is nothing, no horizontal force at all. So no horizontal force means HB equal to 0. Okay, so 3 reaction force, 3 equation, total Mx equal to 0, Fy equal to 0, Fx equal to 0. So you solve these 3 unknown. Okay, so the sequence, you start with calculate moment, and then Fy, and then Fx. That's it. Okay, so for tutorial 3, you're gonna try that yourself. Okay, so you have a force at A, you have a support A, pin support, roller support at E. You have force applied at C, D, okay, with uniform distributed load. Okay, and also 2 kilonewton at point B. So you will have to do it yourself, and then here I provided the solutions. Okay, so you try it yourself, and then you will get this answer. Rax equal to negative 2 kilonewton, Ray at 0.8, Rcy at 0.8, and MC is 6 kilonewton meter, Rey is 11.2, Rdy is 11.2 kilonewton, and Nd equal to 0. Okay, so now we go through the shear force diagram and bending moment diagram, SFD and BMD, the short form. Okay, so why we need this shear force and bending moment diagram? Okay, so you imagine you have a force applied on it. Okay, so how it is gonna react when you have force applied here? how much is the shear force, how to imagine the shear force, okay, know the curve on it, and then how it bend. Okay, so by logic you know lah, when you apply the load on here, so this beam will bend downward here. Okay, so also you can see from this, you have a roller support here, roller pin support here. When you have a load applied like this, so here is going to bend down, and here is going upward moment positive, because when you push something at here will affect it going upward. Okay, so shear force and bending moment. Okay, shear force, the V, you can see the V here at a section is the total algebra force taken only at one side of the sections. Any sections can be taken to be total provided that both sections must have the same values and they follow the marking directions. Okay, so when you have a beam, you can cut at any section. Okay, so when you cut any section, so you will have a photo like this. Okay, so here you have a V. Okay, because it's in equilibrium, so here you have V going downward, here you will have a V going upward. Okay, M also the same, so one is counterclockwise, one is clockwise. Okay, so bending moment is the total algebra of the moment force acting on the sections. So basically you cut at the sections, then when you plot, so you will have this image. Okay, so you can see from this picture, so you have support A, support B, and then this is distance X to the cut sections, and then you have P1 at here, so you will have a V going downward here, V going upward here, moment at here. Okay, so to make sure the beam is in a balanced vertical directions, there should be existing V force that balance the RA forces. Means that when you have a RA, when you cut, they will have a force that balance it. Okay, and one moment M with anti-clockwise. Okay, anti-clockwise move to prevent the beam from rotating. Okay, so both the force and moment must be balanced on the section that has been cut. So the total force and moment at this section is equal to 0. Okay, so when you cut here, the moment will be at here. So you need to something to balance it. Okay, to balance it, is if not, then this section will be bent over. Okay, so make it stable. So when you have a RA go this direction, you will have a force going this direction and a moment to balance it. So the force is known as the shear force, and the force that caused the moment to slide, okay, to bend, to slide into two sections. Meanwhile, the moment is known as the bending, okay, the bending moment, which is the reaction moment at certain points for all forces, as well as combined reaction on the left or the right side, toward this side or toward this side. Okay, when you cut, the left and right must be in equilibrium. So natural sign for shear force and bending moment. So common signs, horizontal direction, okay, to the right is positive, normally we assume. Okay, vertical to the going outward is positive, going downward is negative. So moment direction, clockwise positive. Okay, normally we going clockwise positive and counterclockwise negative, like this. Okay, you can assume like the previous example also, but stick with one. Either if you want to use this, you use this. Okay, so shear force and bending moment according to the forces. Okay, so this is type of loading. Okay, this is the beam, simply supported beam. Rasuk terlepas mudah, simply supported. Okay, this is the shear force diagram. This is the bending moment diagram. Okay, so this is the point load. So when you have point load applied from AFA to FB, okay, simply supported beam, okay, with, you can see the force here, okay, 2 point here. So for the point load, it will cause the shear, the rectangular shape of the shear force. We'll start with positive, you have the force, then going this way, going down, and then like this. Point load only rectangular shape. Okay. Let me clear, okay. And then the shear force diagram, when you calculate the area towards here, okay, later you will learn the area method to calculate, to plot this shear force diagram and bending moment diagram. Okay, so you will turn to this triangular shape. You need to remember the shape, easier for you to do the calculation. Point load is rectangular shape for this, and for the shear force bending moment diagram, and also trapezium side, not trapezium, triangle shape for the moment bending moment diagram. So this is point load. Okay, so for UDL, uniform distributed load, okay, so the shear force will be in triangular shape, positive and negative, like this. And then the moment will have a curve. So just now this one is without curve, this is straight line, this is curve. Okay, so for the moment you will add one direction only. Okay, and then it will cause the triangular shape also. Okay, so this one you will be more understand when you do it in the example yourself, but you need to remember the shapes, okay, when you do the calculations, because when you do the calculation you will get the values, so you can plot. Okay, so procedure to draw shear force and bending moment diagram. So first you need to get the support reactions. You need to determine all the reaction force, like the example before that I explained to you how to determine the reaction force at support. And then you need to know the shear force and moment function. Specify separate coordinates x having the origins from the beam and the left. Okay, extend to the region of the beam between the concentrated force or the couple moments. At sections, okay, you at each section, then you need to cut, and then you calculate lah. So after you get the value, you plot the free body diagram of one of those segments. So shear and bending moment diagram, okay, you plot the shear diagram and bending moment diagram. This one normally we call it SFD, BMD. Okay, in the if the numerical values of the function described V and M are positive, the value are plotted above the x direction. When negative values are plotted below the axis. It's convenient to show the shear and moment diagram, okay, below the free body diagram of the beam. Okay, so this is the example 1, equations and diagram of shear force bending moment diagram for this beam. Okay, simply supported beam. Here you have a beam here, okay, 10 kilonewtons at 3 meters from the A. So first, to get the moment V and moment equations, make the section on each part between the point load, distributed load and support. Okay, so you calculate total ML equal to 0, you get RB equal to 6 kilonewton. You calculate total Fy equal to 0, you get Ra equal to 4 kilonewton. You get Fy equal to 0, H equal to 0. Okay, so when you plot the graph, when you plot this, okay, A, B, 3, 2. So you get A, B, okay, this is 10 kilonewton, 3 meter, 2 meter. Okay, so this is 4 kilonewton, this is 6 kilonewton. So when you cut first, you cut before the load applied. So when you have a 10 kilonewton at here, you cut before and you cut after. Okay, so this is A, this is A, this is B, you cut. So A, X is in between 0 to 3, right before the force. So you can see that here, total Fx equal to 0, okay, M equal to 0. V equal to 4, total M equal to 4 times 0. Okay, so this one you can see that you get this equation, total Fy equal to 0, V equal to 4 kilonewton. V won't change. Total M equal to 0, M equal to 4 kilonewton times the x distance. We know that moment is force times distance, right? The point load times the distance, because it's causing the moment. Okay, so it's 4 times x kilonewton. Okay, total mx equal to 0. Okay, so and also this one you can see is going this way, so we assume going the moment is equal to 0. Okay, so this one is actually, if you calculate moment, minus 4 kilonewton times x equal to 0. So moment equal to 4x kilonewton meter. So when you want to plot the graph, you put x equal to 0 and x equal to 3. Then you insert the value v is equal to 4 kilonewton. Okay, and then when x equal to 0, m equal to 0. When x at 3, v equal to 4 because it's constant, m equal to 4 times 3, so equal to 12 kilonewton. So at x in between 3 to 5 kilonewton, you plot this one. As I said, it's at the b sections. Okay, so you draw this, you get the formula of total Fy equal to 0. Going upward direction is positive. V, okay, V minus 10 equal to 4 minus 10, sorry, 4 minus 10. So you have 4 going upward, 10 going downward. So 4 minus 10 equal to 6 kilonewton. Okay, and then m equal to 4 times x. Okay, 4 times x minus 3 times x minus 3. So this equation. So this one actually is not straight away get this. You have the basic one to calculate. Okay, and then you rearrange become this. So for example, the v here, okay, is actually negative v minus 10 plus 4 equal to 0. So v is equal to minus 6. Okay, if you want to calculate this way. So moment also the same thing. Okay, you're using this, and then you list out everything, you will get this. So you insert this x equal to 3 and x equal to 5 using these two equations. You will get v is equal to minus 6 kilonewton, m is equal to 12 kilonewton. And at x is equal to 5, v is equal to 6 kilonewton, negative 6 kilonewton because it's constant, and moment equal to 0 at x equal to 5. So after you obtain all this, you draw the free body diagram. Okay, normally we will draw at the same directions. Here, okay, you plot. So here is the point 10 kilonewton, here is 6 kilonewton, here is 4 kilonewton, distance is 3 meter, 2 meter. Okay, so when you plot this, okay, you insert the value. Okay, at 0 to 3, you from first one, the v is constant at 4. And then from this is a 0x03. So this is 3x5. You put the value, you get this. Okay, so when from the previous slide you can see for the moment 0 to 12, 12 to 0. So 0 at 0 kilonewton, at 0 meter, at 3 kilometer, at 3 meter is 12, and then at the support B 2 kilo at 5 newton at 5 meter here is 0. So you plot graph shear force and bending moment, you get this graph. Okay, so this is actually, you should have a kilonewton meter here, and this is kilonewton here for the unit. Okay, so this is basically how you draw by using the cut section. You cut at the section before the force and after the force. For this, when apply one load on it. Okay, so if you have distributed uniform load acting on simply supported beam, so how you're gonna do it? Okay, so for the first step, you will have to calculate the reaction RB, RA, okay, and HA. So this one, after you obtain this, you will get the value. So here is 50 kilonewton. Here is 50 kilonewton. Okay, and then HA is 0. HA equal to 0. Okay, so again you cut the sections. Okay, so this one is uniform distributed load, so you cut right before the support B. Only you cut one time. Okay, 0 to x to 10. So when you cut it, then you generate the equations at here at this point. Total Fx equal to 0. So the V is equal to 50 minus 10 kilonewton. Okay, so 50 minus 10 times x. So moment is equal to 50x, 50 times x, okay, minus 10 times x power of 2 over 2, because it's 10 times the x and then times the x over 2. Okay, so this is the formula for the uniform distributed, the rectangular shape, the uniform load, not the triangle distributed load. Okay, so after that you have to key in the value. Let me clear this first. Okay, after that you need to calculate the value. F equal to 0 and Fx equal to 0, x equal to 10. You insert the value, you get V, you get moment. Okay, so after that you plot the shear force and bending moment diagram. Okay, so you can see that the above equation shows that the shear force caused by the distributed load will change linearly with x. Okay, so shear force need to draw first to see the relations with the BMD. So from the, okay, after that you draw this. So again you will have to draw the beam towards here, uniform load. Okay, so you put 50 kilonewton here, 50 kilonewton here. This is 10 kilonewton per meter. Okay, so when you have a 50 V, so this is V, 50 at 0 and negative 50 at here. So we know that from the figure before, from this one. Okay, so from the list load you have the positive and negative here. Okay, so you plot it, positive and negative here, then you connect it, you will have 0 at 5.0. okay, because at here is at the distance, so at the middle, because this is same value 50 and 50. If this is different value, so if let's say you have other force combined together, then you need to calculate, you need to plot and then get the distance. Okay, not just assume to be at the middle. And then you will calculate the moment by using this area method if you are using the area. So now you can see that this moment, okay, this moment at left at x equal to 0 and x equal to 10 is both 0. So how you can plot it? Okay, so distance x, shear force and uniform distributed load is, okay, 50 times over 10 is 5 meters. So see the relations between this point, the equation bending moment. So you get 5. Okay, this one you key in x equal to 5. So when you put in x equal to 5 meter, okay, m equal to 125 kilonewton. So by logic also you know it's happened at the 5 meter. Okay, because when you plot also this is 0, so normally we'll take at here to calculate the moment because it's changed. So this is causing by the positive, this is by the positive shear force. Okay, and then this one is when you calculate the area, this is from negative, it's going 0. Later when you learn the area method, you will be more clear about this diagram. Okay, so when you calculate, you get the area, get the distance x at certain distance. You can get, if you key in x at 4, you get the value for the force for the bending moment diagram at 4 meter, 3 meter, 2 meter, and also you can calculate this by using that equation, by using this equation. Okay, so you calculate, you plot, done. Okay, so from this, okay, therefore the maximum bending moment happens at the shear force is 0, okay, at the central point, and then the bending moment is 125 kilonewton, and then it's in curved shape. when for the uniform distributed load, the bending moment is curved, and then the shear force diagram is triangular shape. Okay, so when you plot it, okay, so this one when you plot it, it must be in a straight line, same line lah. Okay, and then you mention this is a positive direction, this is negative, and then it's kilonewton, and then this is kilonewton meter for the unit, and then this is positive. If you want to draw like this, but you mention this is positive, also can, no problem. Okay, both are correct. Okay, so uniform increased load acting on simply supported beam. Okay, so this one you can see this is a triangular shape. Okay, so you calculate the MA, FY, FX equal to 0. Okay, then you will get RB, RA, HA equal to 0. So how to obtain this, you have learned in static and dynamic before. You can also recalculate based on this equation. You can go through it. Okay, I will go to focus at the shear force and bending moment diagram. Okay, so after that also you start to generate the equation you cut before the reaction force here. So you can see this is the diagram. Okay, so when you do this, okay, then you calculate according to this, you will get the equation of V and M. Okay, so again at the same thing, you calculate the reaction force at X equal to Z. You can see that here you calculate a lot, so you want to see the graph. So X equal to 0, 2, 4, 6, 8, 9. Okay, then you will have to plot the graph. You can see the graph. Okay, so this is shear force diagram, this is bending moment diagram. Okay, and then actually for this one we have a lot of examples. So due to time constraint, I cannot explain one by one. It will take forever. Okay, but then here is example for you, and then I already explained the basic. Okay, for the foundation for you, supposedly you can follow this example lah. Okay, how you get this, go through it, do your revision. Okay, so point load acting on cantilever. Okay, so this is when you have cantilever beam. Here is a fixed support, so this is fixed support. Okay, you have RA, HA and moment. Okay, so you have 10 kilonewton at here. So you calculate the reaction force RA, HA and the moment. Okay, you get the value. So after you get these three value, you insert it, then you start to calculate. You cut at here and cut at here. So this is the first cutting, so you cut, and then you see 0 to X to 8, and then you generate the equations for V and M. You will get the value, and X in between 8 to 10, you generate the equations, and then you get the value. So after you get the value, you plot the graph. That's it. Voila. Okay, so this is another example. You can go through. Okay, and then this is also this is how this is same example lah. You calculate it. Okay, so you can see that when you have several types of distribution load acting on the beam. Okay, so you need to same step but more more complicated because you have more forces. So you need to calculate RA, RB, HA, same thing, and then you need to cut at all before the load. You need to cut. Okay, you cut 0 to in between 0 to 2, 2 to X, 2 to X in between 2 to 4, X in between 4 to 6, at between 6 to 8, and then X in between 8 to 12. Okay, and then so after that you calculate, and then this one is from this direction. When you going this way is 2 root, then you can cut from here. Okay, you can see, you can go through, okay, one by one, and then you get the value of this. But using the cut section, if you calculate by cut section one by one, you would consume too much of time, because you can see, okay, at here you need to cut one, but so you cut, and then you cut, and then you cut, you cut, you cut. How many times you need to generate these equations? You need to do this equation, you need to generate this equation, and then this long equation. Okay, you see the equation is so long. You can see you need to cut so many times to obtain this. Okay, to obtain this. Okay, so let's go through the example with area method. You have, after you calculate the force, okay, at B and at F here, you get the force, okay, and then you can start to use the area method. So we start from here, A to G, one by one we go through. Okay, so you can see the first, at point A here, no force and no point load because it's free end. So you start at 0. After you start at 0, you can see that, okay, at point V, you have a UDL, 20 kilonewton. So this is going downward is negative. So 0 minus 20 plus 20 multiply 2. So you get negative 40. So you're going downward, you get 40. Okay, 40. Then you at point V, you see you have 129 kilonewton going upwards. So negative 40 plus 129, you get 89. So you plot, you get 89 here. After you get 89 here, okay, you go to point C. Now point C, you have a UDL 20 kilonewton, 2 meter. So 89, okay, at point here, you carry here, minus 40, you get 49. So you plot, you get this value. Okay, so 49, you plot this value, and then at point D here, you going this way. Okay, no other force, no any force here. So remain the same. But then when you see the point load at the previous slide, point load at the point, you will have load, right? So 40 minus, okay, 40 minus 75, you get 26. Negative 26. Negative 26, sorry, at here. So negative 26 at here. Okay, this one is this BD. Okay, so 26 at here, you go through the point E, no load at here. Okay, so it's no load. So remain 26 at point E here. So after point E, you move to point F. Point F, you have a triangular shape of this loading, and also, but then the moment at here, you at point E have a shear force, have a moment, but the moment at shear force bending moment diagram is not calculate because it's moment. You don't have shear force on it. Okay, so after 26, okay, you go to the point F. Okay, point F is VE. Okay, 26 minus 26, negative 26, plus 30 times 4 over 2. Okay, 30 times 4. The distance over 2, the area of it. Okay, so you get the value is 86. My negative 86 here. So this is negative 86. So when you move to here, you can see the 86 here. At here, you still have 1 point load at F. So negative 86 plus 135, 136, you get 50. So you draw at here 50 point for this one. Okay, for this. And then you go to here, 50 kilonewton. At here to here, there's no any forces, so remain the same 50. So 50, you have a 50 going downward. Okay, so 50 minus 50, you get 0. So case closed. So if you draw by using area method, if at the end you didn't get 0 value, so it's incorrect. It must be balanced. Okay, so after you get the shear force diagram, you calculate the bending moment. So bending moment diagram is basically you calculate this area. Okay, you calculate this area, and then become the bending moment diagram. Okay, so let me continue. Okay, so bending moment diagram, you calculate from this A. Okay, you calculate also A, B, C, D, E, F, G. By right, you draw in one row lah, but this is a stacked row, so no space for it. So it break it to 2 parts. So you calculate the area A, you get 0 here. So MB is equal to MA plus the shear force diagram. MA, there is no any moment at here. Okay, so it's 0. So at B, okay, is 0 plus, you can see this is a triangular shape for 40 kilonewton. So the area is 1/2 times 2 times negative 40, so you get negative 40 kilonewton. Okay, so MC is equal to MB. So you carry forward here. For negative 40 plus, so this is positive, right? 89, 40. This is a area for it. So you calculate this area, you get 98 kilonewton meter. Okay, so you calculate this plus this. So at point D, so this one is C. You get A, B, C. So you get D, E, F, G, F, S. Where is F? F is here, sorry. F is here. Okay, so you calculate MD. Okay, is the area. You can calculate, you see the area of this is 49 times 2, the distance, the this value times this distance. Okay, you get this. Okay, so 196 you carry to this ME. Okay, you must carry all from the previous value. You can see this is all carry from 196 minus 26 times 2. So this is the at the negative part, so it must be negative lah. You minus 26 times 2, so you get 144. So you plot 144. But then at 144, you can see here you have a moment 30 kilonewton. So you need to be alert. This is not included inside here. No, nothing at here. So you need to remember you have a moment at here. So 30 kilonewton. Okay, so the direction is going counterclockwise, so it's negative. So you get this 114, this value 114, ME here. Okay, 114. So 114, you go to calculate this one, you get the area for this. So to calculate area for this, you're using this equation. Okay, so for this section, you calculate using the rectangular, the area, and then this one you're using the triangular shape, and then at the centroid for 1/3. Okay, for 1/3 here, minus the rectangular shape, minus the 1/3 side, you get this. Okay, this is the bottom part, so you get negative 150 kilonewton meter. Okay, so for MF, so you get this. So 150 plus the area, you can see this is positive. Okay, and then this distance is 3. So negative 150 plus 50 times 3, you get 0. So balance. Here 0, here 0. Okay, so this is area method. Thank you.